stuck in another week of quarantine. Boredom creeping in, loneliness perhaps. But to this I say, it is what it is.
It is what it is.
Welcome back to the third official Corona Chemistry video where we will be tackling the topic of periodicity, otherwise known as trends of the periodic table. You can find the topics that we are tracking minute by minute directly above my face right here. We'll be highlighting the topics that we are covering at that given point, so you can scroll through the video to your ease. And then be sure to grab the link that follows the slides and the notes that we are covering in this video directly below this video. Here-ish or so. New to this setup, new to video making in general, so here we go. To understand the trends that we'll be discussing today actually only boils down to two different causes for each of the trends. And those trends are known as effective nuclear charge and shielding. And so we'll go into a little bit of detail as to what these terms actually mean and how we can actually calculate effective nuclear charge, for example. Well, if you can imagine, the atom, of course, is made up of nucleus and the electron cloud, and the nucleus in the center is densely packed protons and neutrons. And the most important part about the nucleus is that it has that positive charge from the protons. Well, that positive charge attracts the electrons swirling and dancing around in the outside of the cloud. And so the stronger your nucleus is, the greater an influence it has. And so your effective nuclear charge is just how much pull that positively charged nucleus has on its negatively charged electrons. And we can actually mathematically calculate it using the formula ZEF. This is the nomenclature they use for effective nuclear charge, is equal to the number of protons minus your inner electrons. We'll do a couple of examples with that here in a little bit. In shielding, every time we go down a row on the periodic table, say from sodium to potassium, we are actually adding another ring of electrons there, therefore increasing the distance between the nucleus and its valence electrons, the outermost electrons of this atom. And when we do that, we are increasing a factor that is known as shielding, the distance between the nucleus and its outermost electron. We'll get a little bit more of a visualization with that here in a little bit. But how do we calculate the effective nuclear charge? Well, once again, the effective nuclear charge is simply your protons minus your inner electrons. Well, when it boils down to it, for all neutral atoms, it's actually a very simple calculation. Your effective nuclear charge will actually always be equal to the number of valence electrons that neutral atom has. And so, if you recall the information that we instilled with you in the last video with electron configuration, column 1A, the alkali metals, all have one valence electron. Column 2A, two valence electrons. Boron's family, 3 valence electrons. Carbon, 4 valence electrons. Nitrogen, 5. Oxygen, 6. Fluorine, 7. And we're talking about oxygen family and the halogens, not just fluorine itself, but the entire family of the halogens with fluorine, 7 valence electrons. And then, of course, your noble gases have that full octet, 8 valence electrons. They also have that same effective nuclear charge, +1 through +8 for each of those respective families. But we want to actually understand how we actually arrive to that conclusion, and that is by utilizing the calculation protons minus inner electrons. But what if it's not a neutral atom? Oh my goodness. What's going to occur? Does the effective nuclear charge increase, decrease, stay the same? I don't know. What if we are tasked to calculate the effective nuclear charge of Na+, a sodium cation? Well, on our next slide here, we have the neutral sodium in all of its glory, 11 protons, 11 electrons. And notice that there are 3 rings of electrons, only 1 electron on the outside ring, 1 valence electron, exactly as we expected. And whatever reaction this sodium undergoes, it becomes an Na+, a sodium cation. And now it only has 2 rings of electrons. Well, now this second ring of electrons is the outer ring of electrons. Therefore, there's only 2 inner electrons to work with. And so our calculation looks a little different because our number of inner electrons has absolutely changed. And so to calculate the effective nuclear charge for a sodium cation, it's still my 11 protons. That did not change. As long as I'm sodium, I'm always going to have 11 protons, minus only 2 inner electrons now. And so my effective nuclear charge becomes +9. That is a difference of 8. Sodium neutral has an effective nuclear charge of +1, but the sodium cation has an effective nuclear charge of +9. And so go back to our previous slide, and we see this question right here, aluminum 3+. Well, neutral aluminum because he's in that boron family, has 3 valence electrons, and therefore would have an effective nuclear charge of +3. If we're looking at Al3+, the aluminum cation, all we have to do is add 8 to that. And so therefore the effective nuclear charge of an aluminum cation would therefore become +11. So that's effective nuclear charge. Now let's get the visual of shielding a little bit further. So remember what we said, every time we go down a row on the periodic table, we're adding another ring of electrons. So for example, sodium neutral, the neutral sodium atom has 3 rings of electron. Therefore, potassium would have 4, rubidium 5, cesium 6, francium 7. Well, if we look at this picture, this Bohr model of whatever atom we're looking at here, it doesn't actually matter. All of these electrons swimming around in the cloud are all negatively charged. And Paul Abdul in her Hit 90 single says that opposites attract, but like charges certainly repel. And so the fact that all of these electrons are negatively charged means that these guys do not want to be next to each other. Therefore, there's a little bit of repulsion occurring. They're pushing each other away from one another. They're getting as far apart from each other as possible, which means every time you add another ring, you add another layer of that electron-to-electron repulsion that they're experiencing, pushing them further and further and further away from the nucleus. Right? This is home. This is mama. And the further and further you get away, the less pull you're going to feel from mama in the center. So that is shielding. Another way that I really like to look at it, I'm a big football guy. Big football guy. I like to look at it as a kickoff return. Right? Here's my valence electron. And here's the nucleus trying to get to the valence electron, which if you know football, then what is occurring here is this is the kickoff, and we're attempting to return it for a touchdown. Doesn't typically happen because we're going to get tackled by all of these guys at some point down the field, right? Anyways, we're fielding this kick, and each of these players in between my returner and this nucleus up here at the top is another layer of defense for my runner, right? So here in this situation, this guy wants to be as far apart from these as possible. Meanwhile, in our visual of the atom, right, in our visual of the atom, the electron wants to feel the pull from the nucleus. It's attracted to the positive charge of the nucleus. However, the further and further and further it gets away, the less it actually experiences. Okay? So that is a summation of effective nuclear charge and electron shielding, the explanation for all of the trends that we will be discussing today. So typically the questions that we are faced with these trends is we are asked to compare the one element to another, or maybe just simply give the summation, the summary of what kind of trend we're going to see as we move from one direction to another on the periodic table. Top to bottom, left to right is typically how it's asked, and that's how we're going to show it in the video today. That's how we're going to describe it. Yes, there are blips to most of these trends, little blips, but overall, as we move from left to right, we're going to see one overall change, and as we move from top to bottom, we're going to see one overall change. And the first trend that we're going to examine is actually the size of the atom. We're going to start with atomic radius, and then we'll talk about radius or radii of the ions and the changes they experience when they lose or gain electrons. Anyways, starting with atomic radius, the radius is going to decrease as we move from left to right. Now, you could simply memorize that, right? Or if you understand how those two reasons, effective nuclear charge and shielding, apply to this, well, then there's no need to actually memorize it because you can understand it and you can internalize the meaning behind this. Well, as I'm going from left to right on the periodic table, what am I adding? Right? As I move from sodium to chlorine on the periodic table in period 3, what am I adding every time I move one space to the right? Yes, I'm adding neutrons. Yes, I'm adding electrons. But most importantly, I'm adding protons. Right? And the more protons I add, the stronger I become. The stronger I become. So when I compare these two elements, what kind of visual could we work with here? Sodium and chlorine. Chlorine's got 6 more protons. Yes, more neutrons. Yes, more electrons. But most importantly, 6 more protons than sodium. Stronger. And so what we've got here, 2 different strapping young lads. Both great in their own right, but different. We've got sodium on the left. I'm going to call him Timmy. He's a scrawny guy. He means well. And then I got Tony on the right. Tony. Tony is wow, he's chiseled. He's worked for that physique. Strong. And so, what we think when we're moving from left to right, what changes are occurring? Well, who can hold you closer at night? Timmy or Tony? Timmy or Tony? I feel like if you hug Timmy, you might break a bone. His hips might poke you in the side. He might stab you with his hip bone. But Tony, he brings you nice and close, wraps you with his tree trunk arms, and you feel safe. You feel warm. And so as I'm moving from left to right on the periodic table, as I'm adding these protons, I'm increasing the strength of the nucleus. Therefore, the more strength that they can actually pull these electrons in with. And so as I move from left to right, I am going to see a net decrease in the radius. And yes, there's small hiccups. If you were to examine this whole chart right here, I just pulled this diagram off Google. Yes, there's hiccups and blips in the trend. Don't focus on that. Overall, as you move from left to right, what do you see? You see the atom getting smaller. Well, as I move from top to bottom, what are you going to see? Well, just think about it. I feel like this is one of the more obvious trends. As you move from top to bottom, you're literally adding more stuff, right? If you were to add more weight, you would get bigger, right? As a human being, as a person. And so, as I'm moving from top to bottom, the most important thing that I add every single time is I add another ring of electrons, right? Lithium has 2 rings of electrons, sodium has 3, potassium has 4, rubidium has 5, cesium 6. Every time you move down a period on the periodic table, you add another ring of electrons. And of course, if you're adding another ring from the center, your atom, of course, is getting larger. But what are we going to draw upon? It's the fact that the shielding is increasing. I'm adding another layer of electrons in between the valence electrons and the nucleus. I am increasing the shielding, therefore increasing the distance from the nucleus and the valence electrons, therefore increasing the size of my atom. So let's move right along to ionic radius here. What is going to occur when I lose or when I gain electrons, right? Metals typically lose and become cations, positively charged ions, and nonmetals typically gain electrons and become negatively charged anions. Well, what's going to happen when they lose or when they gain? Well, think about it. If you've got siblings at home, this might be a pretty easy visual. I remember myself, the oldest of 3 boys in my family, getting all the love from my parents when I was the only child, but when my brothers came along, well, now that same love that my parents had to give was now spread between 3 boys. Okay? Or maybe you can think of this as the perspective as the youngest kid. Right? When you were the youngest kid, I'm sure that your older brother or your sister went away to band camp or church camp or something in the summers. Either way, it left you as possibly the only child remaining at home. Well, what happens? Right? You're sitting at home alone, or you think you're home alone, your parents are somewhere else in the house, or you're just minding your own business, you're playing Bejeweled on your phone, you're playing Clash of Clans, whatever you got going on, but brother and sister have gone away to camp, the only child left at home, and now what is it? They don't get out of your business. Mom, get out of my face! Dad, get out of my face! Now, of course, these aren't my parents. These are just parents that I got off Google. But your leash is a whole lot smaller. Now they want to know what you're doing every waking moment. Oh, did you talk to that pretty girl at school today? Right? Did she text you back? Oh my God, what would you like for dinner? Would you like Chili's? Chili's is your favorite. Mom, we've had it 3 times this week. Come on. You're spoiling me. But notice, the less kids that they have to take care of, the smaller the leash is. Because now the love that was previously spread between all of these kids is now focused on the 1 or maybe 2 kids that's remaining at home. And so that same amount of love that was spread between, 3 or 4 or 5 kids, whatever your situation is at home, is now honed in on whoever's remaining. And so that same amount of strength, that same amount of love is put into that 1 kid remaining. Therefore, it gets smaller and smaller and smaller. And so when it comes to cations, the more electrons that you lose, the smaller you become. Notice, looking at sodium to magnesium to aluminum, the red is the actual cation. The gray is what they were before when they were neutral. They're getting smaller and smaller and smaller. Sodium loses 1 electron, magnesium loses 2, aluminum loses 3. And so the aluminum cation, compared to all 3 of these elements, is absolutely the smallest. Well, the exact opposite occurs for anions. I remember, once again, going back to when I was the only child, playing alone, out in the front yard. And I would kick my ball out into the street. And my mom, who was previously sipping on a sparkling water on the front porch, if I kicked my ball out into the street and I was about to go and fetch it and retrieve it so I could resume my play, she would yell at me, "No!" Oh my goodness. She would have to go and cross the street and get the ball herself. But when my little brother came along, she had to focus on little baby. When she had to focus on little baby, my leash got a little longer. She had to give her attention elsewhere sometimes. Well, when I kicked my ball across the street, I looked back and forth to make sure she wasn't watching. I slowly tiptoed. Of course, I looked both ways before crossing the road, and I got away with playing in the front yard across the street. Why? Because my leash was a little longer. The more electrons you gain, the larger the atom becomes. Being an element, you have a number of protons that determines what element you are. You cannot change that number of protons. And so, we're changing the number of electrons. We're not changing the number of protons. We're not changing the strength of the nucleus. That can never change. And so, when you put more electrons in the picture that same nucleus has to take care of, well, it widens the leash a little bit. Let's say you're used to walking one dog. You're a dog walking business. You didn't start off that great. You only had one customer, one dog. But suddenly, business starts picking up. And now you got 6 dogs to walk at a time. You went from 1 dog to 6 dogs. Well, I guarantee those 6 dogs are pulling you down the road, right? And so the leashes are probably stretched out to the max. Whenever you had that one dog, it was loose. It was kept at your waist. You didn't have to worry about it. One dog's not going to pull you away. But 5 new dogs that you weren't used to taking care of, same strength, haven't had the time to buff up yet, well, those dogs are going to be pulling you down the street, which is why anions get larger the more electrons you add. And so we've got a couple questions on our notes here. Okay, which group of metals will be the largest after losing electrons? Well, that's the one that loses the least. Your alkali metals will be the largest set of cations, whereas your boron family or your aluminum family will be the smallest family of cations. And so now we go to the next slide, which is going to ask, of course, the exact opposite, right? Which group of nonmetals will be the largest after gaining electrons? It's going to be the group that gains the most electrons, which if we're looking at the periodic table, the nitrogen family wants to gain 3 electrons, and so they will be the largest typically after gaining their electrons. Which group will be the smallest after gaining electrons? Well, the group that only gains 1 electron, and those are your halogens. Now notice, it's pretty close in a lot of these instances, right? I believe they're measuring these in picometers, right? Fluorine minus anion, 119 picometers to 126, 167 to 170, 182 to 184. It's small. It is a small, small difference between these elements, and yet the trend remains true.
Quarantine log. Day 29. I planted some rosemary and basil a couple of weeks ago. Everything online says that it should only take them a few days to sprout. I'm sure mine are just shy, holding on to some hope.
All right, the next trend we'll be examining today on the periodic table is ionization energy, which is defined as how much energy is required to remove an electron from an atom. And here we've got a diagram in front of us which shows us in kilojoules per mole how much energy is actually required to remove an electron from various elements, right? And notice that it's very easy to track that these are the periods on the periodic table. These are different rows. For example, this is row 2. We've got lithium, which appears to be the lowest, and fluorine and neon up here at the tippy top. Notice our noble gases very, very, very high up. Once again, ionization energy, how much energy is required to remove an electron? Well, what is the explanation for the trend that we see? How can we tie this back to effective nuclear charge and shielding? Well, as we're moving from left to right on the periodic table, once again, what are we changing? Right? What are we changing? We are adding a proton every time we shift one space to the right. When we're moving from sodium to magnesium, we add 1 proton. When we're going from sodium to chlorine, that's right, they're coming back, right? Timmy and Tony, right? We have a difference of 6 protons. And let's say you go on a date with each of these gentlemen. You go and see a movie, okay? And you're coming out of the movie theater, right? and a guy comes and tries to grab you. He says, I'm taking this person. Whether you like it or not, Timmy slash Tony. Well, who would you rather be in this situation with at that given point? Timmy or Tony? Timmy or Tony? Timmy, once again, feels like if you touch him, he'll shatter into a million pieces. Tony, strapping physique. Great size. I guarantee when you're walking out of the movie theater, his arms around you, no one's going to threaten to come and snatch you up if you're with Timmy. Good luck out there. I don't think Timmy would fight for you. I think Timmy would say deuces and banana split out of there. I don't know. So as I move right on the periodic table, because I'm increasing the effective nuclear charge, aka the strength of my nucleus, it becomes harder and harder and harder to remove that electron. Which is why, generally, yes, there's a few blips in the trend, and that can come, we'll explain that in a different video if we find that to be necessary. As we move from left to right on the periodic table, we see that our ionization increases. And yet, as we move down, what are we going to see? Well, let's go back to our visual here. As we go down on the periodic table, what do we see with our ionization energy? Does it get easier or harder to remove that electron? For that, we require another visual. A nice peaceful playground, right? And let's just say, for the sake of this visual, that this is all one family, the Jefferson family. We've got mom over there on the park bench, and we've got 1, 2, 3, 4, 5, 6, 7, 8 kids. Wow. The Jeffersons have 8 kids. Mommy has obviously selected her favorite, as that's the one who's sitting on the park bench with her. Everyone else is having a great time, though. Okay, everyone else is having a great time. But, what's this? What's this? A van rolls up to the park. On the side of this van, it says free chemistry and candy. Oh my goodness, what are the intentions of this van driver? Well, it would appear that this van driver wants to come away with this situation with one more kid than he's coming in with. Now, I'm not saying this is my story. I'm just saying this is a scenario that could possibly happen. Well, by golly, which kid is this van driver going to take? Are we going to take Sally all the way over there on the park bench with mom? No. You see, this is a well-conceived plan. The van driver's been plotting this, watching the Jefferson family for weeks, and he has concocted that it's little Jeffrey on the swing set, way on the outside, that is the optimal target. Why? Well, think of each of these kids as a separate ring of electrons. Which one's the easiest to snag? If mom is the nucleus, mama nucleus, which one is the easiest to snag? Well, of course, it's little Jeffrey on the swing set. He's the furthest away from mother's love. In fact, every kid in between Jeffrey and mom is another layer of shielding. Oh my gosh, there's no guarantee the mom can even see Jeffrey. With 7 other kids in between her and Jeffrey, I'm in and out in 12 seconds. And I come away mission successful, mission accomplished. Jeffrey is in the back of the van. Now, I'm sure they're going to live a long and prosperous life. I don't know what the aftermath of this scenario is, but all I know is that I have chosen the optimal target for which I'm going to set my sights on. Going back to our visual here. As we're moving right on the periodic table, which we can see here, let's just pay attention to the alkali metals here at the bottom. Pretty comparable. However, it's very obvious that it's dipping down the slightest bit every single time. Lithium to sodium to potassium to rubidium to cesium. Even though it's a small difference, but it's a difference nonetheless. We're seeing that it is easier to take from cesium than it is from lithium. Well, look at their position on the periodic table. Lithium's in row 2, period 2 of the periodic table, and cesium is in period 6 of the periodic table. That's 6 rings of electron versus just 2 rings of electron. It's very dangerous to take a kid when it's sitting right next to its mom. Not as dangerous to take it when it's sitting, 50 yards from its mom. I am not advocating for this, by the way. Absolutely not. But if I were going to engage in such a mission, so to speak, you've seen my plan. And it's all founded on chemistry evidence. Thank you. But now, to further explore this topic, which group would have the lowest second ionization energy? Which group would have the highest second ionization energy? Well, what that means is how much energy would be required to remove a second electron. Just like if we were to say, what would the third ionization be? That's how much energy would be required to take a third electron from that atom. Well, if you're taking a second electron, that's going with the assumption that you've already lost one electron. Well, which group would not want to lose a second electron? And for that, we're going to make sure that we look at the positioning of this family and these elements on the periodic table themselves, right? Which group would be the most resistant to losing a second electron? Well, in order to analyze that, let's go back to this slide. Which group is the most resistant on losing one electron? Well, it's all of these guys. Our noble gases. Why? Because they are already happy and stable. In previous units of chemistry and previous concept of chemistry, we know that the element is most stable when it has a full valence octet of electrons. Well, the noble gases have done that. And just like you as human beings, when you get something good in life, maybe it's a relationship, maybe it's a new car, you're going to be pretty resistant to losing that something good in your life. If it's something that makes you happy, you're not going to let just anyone walk up to you and take it. Absolutely not. Well, now let's ask ourselves, which family achieves happiness after losing one electron? Therefore, would be the most resistant to losing a second electron. Well, that is absolutely going to be your alkali metals family. Lithium, sodium, potassium, rubidium, cesium, francium. They have one valence electron, so that once they lose that one valence electron, they're happy as a clam, which means they would have the highest second ionization energy. The other question is, which group would have the lowest second ionization energy? Well, which group kind of wants you to take that second electron? Not that they're not going to put up a little bit of resistance, right? The nucleus still has some attraction to those electrons, and yet one family kind of wants to part with that second electron more than any other family. Well, looking at it, it has to be the alkaline earth metals family. They are going to have the lowest second ionization energy because once they lose that second electron, they are going to be happy as a clam, 8 valence electrons. Why do the alkali metals have such a high second ionization energy? It's because once they lose that first electron, their effective nuclear charge goes up a lot. As we saw way back earlier in this video, when sodium loses that electron, right, its effective nuclear charge went up by 8, went from +1 to +9. And so that is why the ionization energy just goes up drastically. And that is the explanation for ionization energy.
Quarantine log. Day 32. I've started to try to grow some facial hair. I started about a month ago. I think it's going pretty well. Not much to show for it yet. But, you know, while I'm trapped in here, might as well try a new look.
So the last main topic that we'll be discussing, the last main trend that we'll be discussing is electronegativity, which is defined as the ability of an atom to attract electrons. Well, let's think of the atoms that actually want to attract electrons, because we're actually going to exclude a family. Your noble gases already have that full valence shell. Therefore, they're kind of excluded from this trend. They have a very, very low electronegativity, despite being dangerously close to fluorine. Fluorine is the most electronegative element on the periodic table. The most attractive. That's why Dolly Parton wrote her song, Fluorine, 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 fluorine. Please don't take my man just 'cause you can. Fluorine's dangerous. If she were to walk through this door right now and ask me to come away with her, I would leave my wife for her immediately. That's the power of fluorine. The most electronegative element on the periodic table. the highest ability to attract electrons. And so generally the trend is the further I go from fluorine, the less electronegative I become. Well, if we're looking at the periodic table, the noble gases, especially neon, is right stinking next to it. But neon has a very, very low electronegativity because it doesn't want any more electrons. It already has 8 valence electrons. Therefore, it's not so worried about getting any others. But the trend, for the most part, as I go from left to right on the periodic table, aka closer to fluorine, my electronegativity is going to increase. And as I move down a group on a periodic table, the electronegativity is going to decrease because I'm getting further and further and further from fluorine, so to speak. So very, very important term there, electronegativity. There's a couple other minor trends that we can discuss, and that is metallic character and reactivity. Metallic character is how much of a metal you are, right? The amount of character that you display that is metallic, like, well, think back to your naming unit and compound forming unit. Metals want to lose electrons. And so the best metal is the one that is most willing to lose electrons, the most metalliest metal. The most metalliest metal is the one most willing to lose an electron. And so, if we're looking at the periodic table, the most metalliest metal that I can think of is francium. It's the largest atom that we see in terms of our atomic radius pattern. It's got the most rings, therefore the most shielding. She's, frankly, a terrible mother. Okay? She's kind of like the one we saw in our previous example here. She's got lots of kids to worry about and doesn't really know how to keep up with all of them. So, frankly, that kid on the outside never stood a chance, francium. I'm sorry, Jeffrey. I'm sorry, okay? It is what it is. And so, the further down I go on the periodic table, the more metallic I become, because the shielding is going to increase. Therefore, the easier it is for that metal to give up an electron. And the further right I go on the periodic table, the less my metallic character is, because the stronger my effective nuclear charge becomes. Remember, we're equating all of these trends back to those two terms: effective nuclear charge and shielding. If you can relate everything back to those two terms, then you understand it. If you understand those two terms, then there's no actual need to memorize the left to right, the top to bottom, because you can imagine what's actually happening in your head. I'm adding protons. I'm adding rings. That's the most important part. As I'm moving right on the periodic table, I am adding protons. As I'm moving down on the periodic table, I'm adding rings of electrons. That's the most important part of these trends here. And our last overall trend that we're going to look at is reactivity, how reactive an element is. There's sort of two trends here, one for metals, one for nonmetals. Well, the most reactive metal will be the most metalliest metal, which, as we just discussed, francium. So for metals, as I go down, my reactivity is going to decrease. And as I go right, the stronger my effective nuclear charge is. Therefore, the less reactive I become. So when I'm looking at the periodic table, we've got our metals in family 13, otherwise known as family 3A, right? Those are going to certainly be less reactive than family 1A. But within family 1A, sodium comparing to francium, for example, francium is going to be much more reactive than sodium because francium has much more shielding. Okay? So now, going back to our slide here, for nonmetals, it's as I go from left to right, my reactivity is going to increase. And as I go from top to bottom, my reactivity is going to decrease. Think of fluorine, right? Fluorine, the most attractive, most beautiful element on the periodic table, right? It wants to attract that electron. When it attracts that electron, that is a reaction. And so nonmetals want to gain electrons. And so the one most willing to behave like a nonmetal, aka most willing to gain an electron, is the most reactive nonmetal, aka fluorine. And so, which group on the periodic table contains the most reactive nonmetals? A lot of you looking at that trend on the previous slide might go all the way to the right and go to the noble gases, but remember, the noble gases are also called the inert gases, meaning they don't want to react. They're already happy. And so it's actually the halogens in family 17 that are most reactive family of nonmetals. As I go right for the nonmetals, reactivity is going to increase. And those are all of the trends on the periodic table that are worth talking about. Yeah, there's several other patterns you can look up online, but those are the ones that our curriculum covers, and we wanted to get to you and distribute that information to you. But remember, everything goes back to those two terms. Let me pull them up here again. Everything goes back to effective nuclear charge and shielding. If you understand those, if you ingrain those into your brain, then you're good to go. Then there's no need to actually memorize this little handy-dandy shortcut chart here, right? In this next part of the video, we're just going to go over example problems and how we tackle those. And yes, everything can be solved using this chart right here. However, it's much more beneficial to actually internalize and understand what the heck shielding is, what the heck effective nuclear charge is.
Quarantine log, day 34. I had a few days where happiness was prevailing, but not today. I listened to a song and it really hit me. Didn't even notice the punches that you're throwing. Why are they throwing punches? Why don't you say so?
So now let's tie everything together that we've discussed so far and tackle a few practice problems so that you can see how they are framed and maybe possibly give you a few hints on the line of thinking that you want to take in approaching these problems. And they usually look a lot like this one, having you put a string of substances or species in order from smallest to largest, largest to smallest, highest to lowest, lowest to highest, that sort of thing. Sometimes they even just have you compare two species, that sort of thing. But either way, we're using the same information. This first question is put the following in order from smallest to largest. We have neutral magnesium, magnesium 2 plus cation, aluminum, and aluminum 3 plus cation. And we're going to go off of the trends that we've learned today. Maybe there's a few hiccups in the trend that we're not accounting for. However, we're going to go off of the overall information that we were given on the very first screen. Ionization energy, what's happening as I'm moving from left to right. Ionization energy, what's happening from top to bottom, that sort of thing, right? Yes, there are hiccups in the trend. Yes, we know this, but we're only being held accountable for the overall trends that we're seeing here. So either way, in putting them in order from smallest to largest, we first want to compare the two like substances. So let's compare the two neutral ones together, magnesium versus aluminum. Well, let's look at them on the periodic table and notice that they're in the same period from one another, which is perfect for us because that's how we actually learned the patterns in the first place. As I go from left to right on the periodic table, aka if I move from magnesium to aluminum, what is occurring? Well, as you go from left to right on the periodic table, the overall size of your atom gets smaller. And so by using that logic, by using the logic that we gained from our very first screen, our overall pattern, and our understanding of the increase in effective nuclear charge that's taking place moving from magnesium to aluminum, because aluminum has one more proton, well then we are going to assume that aluminum has a smaller radius than magnesium. So that's going to make aluminum smaller than magnesium. It doesn't make it the smallest, but it certainly makes it smaller than magnesium. So at least we have the locations of two of our species so far. So now let's compare the cations. And actually it might help to analyze magnesium versus Mg2 plus in our question. Oops. It might help to analyze magnesium versus Mg2 plus and aluminum versus Al3 plus. Well, what occurs when we lose electrons? Well, do recall from our ionic radius discussion that when we lose electrons, we still have the same strength of nucleus and yet less things to actually take care of and keep within the orbit of our nucleus. Same strength, less weight to deal with. It's just like when you're in the weight room, right? You're used to lifting 200 pounds, but you're only lifting 100 pounds today. A lot easier for you, right? Absolutely. And so you can bring in those electrons a whole lot tighter. And so that's going to make Mg2 plus a whole lot smaller than magnesium, and that's going to make Al3 plus a whole lot smaller than Al. In general, the cations are much smaller than the neutral atoms in the first place. And so what that's going to do is that's going to put our cations as the two smallest species, and then our two neutral species as the larger. So we've already got our back half, right? Magnesium is going to be the largest, aluminum will be the second largest. But now, how do we compare these two? Well, whoever loses more electrons is going to end up smaller. On top of that, aluminum has more protons than magnesium, therefore this effective nuclear charge is going to be stronger. The pull of the nucleus is going to be stronger than magnesium 2 plus. And so, we get to our answer. La-da! Now, a lot of the time, sometimes they will just give you these four species and they'll simply ask you, out of these four, who's the smallest, who's the largest, that sort of thing. Sometimes they have you put it in order as well. On to the next question. Put the following in order from lowest ionization energy to highest ionization energy. So they're having us tackle and approach a separate trend now. And we have to recall what the definition of ionization energy is to first approach this problem. And ionization energy is the amount of energy is required to steal an electron. The amount of energy that is required to steal an electron. Well, as I go right on the periodic table, my effective nuclear charge is going to increase. And as I go down on the periodic table, my shielding is going to increase. So how do those changing values affect my ionization energy? Well, if you have a stronger pull of the nucleus, it's going to become harder to take the electron. And shielding is going to sort of subtract from that pull of the nucleus. Therefore, it's going to get easier to pull the electron. And so let's look at where all of these elements are taking place. We have barium, fluorine, arsenic, and iron. Okay, so let's go to our periodic table. And they're really all over the map. Barium is in the alkaline earth metals. We have iron in the transition metals. We have arsenic in the nitrogen family. And we have fluorine as a halogen. Well, look at where fluorine is placed, all the way up and to the right. Very, very, very high effective nuclear charge compared to our other substances. Therefore, it's going to be very, very hard to pull the electron away. Very high ionization energy there. Barium on the opposite side of the periodic table. Second column, right? So not moving very far to the right. Therefore, Therefore, the effective nuclear charge not very high. And he also has a significant amount of shielding due to being in the sixth period. So lots of rings of electrons to deal with here. So that would lead me to believe that barium has the lowest ionization energy here, and fluorine would have the highest. Well, where are we going to place iron and arsenic in this? Well, notice that iron and arsenic are on the same period. Fe, number 26, and arsenic over here in the nitrogen family. Iron is a whole lot more to the left. So which means arsenic gets a greater effective nuclear charge, more protons to work with, stronger pull of the nucleus. Therefore, arsenic is going to have a higher ionization energy than iron. It's going to have a stronger pull of the nucleus. Therefore, we get our answer. Ta-da! It usually works better to get your two extremes, your lowest and your highest, and then work on the middle, I would say. Once you get your outsides done, the middle sort of lays itself out. And our final problem that we will do together today, put the following in order from highest electronegativity to lowest electronegativity. This is going to follow the pattern of fluorine being a hot, hot, hot attractive element. Therefore, the closer we get to fluorine, the more electronegative we become. And so we've got nitrogen, cesium, phosphorus, and potassium. We're going to see that these elements are simply in two separate families. Potassium and cesium are in one family, and nitrogen and phosphorus are in a family as well. And so the further you get from fluorine, the less electronegative you become. All we have to look at who's the closest. And this is from highest electronegativity to lowest electronegativity. Always pay attention to the wording in the question. Sometimes they can flip it on you. So just make sure, highlight, underline whatever the direction they're asking you to go for, because it's very easy to flip these. You can have the trends down completely in your head, but very easily flip them as well, and end up getting a question that you know all the material for. You could get it wrong, and that's the biggest sucker punch. So anyways, looking at our periodic table, nitrogen is absolutely the closest to fluorine here, and phosphorus is just below it. So I'm going to put those two at the highest. And then comparing potassium and cesium on the far left. Sorry, working backwards here on this camera. Potassium and cesium, of course, in the alkali metals on that first column on the periodic table. Well, potassium is higher up, therefore not as much shielding is taking place. Cesium having more electron rings to worry about, not as strong of a nucleus in order to emit this attractive pull. Therefore, potassium is going to be a higher electronegativity than cesium. So the order that we're going to rock with here is going to be nitrogen highest, phosphorus second highest, potassium third, and cesium last place. So let's see. And boom, we're good to go. Ladies and gentlemen, that was periodicity, aka periodic trends. Corona Chemistry, out.